Okay, so I want to do a problem that you may have seen something like this, and this one's going to be a little bit more complicated, so it might take a little bit more time. But I want it to be harder than what you would normally see. So in this problem, I have a mass on a spring, and in fact, I'm actually using this actual spring, which I did measure the spring constant for. So this has a unstretched length of 7 centimeters and a spring stiffness of about 5. So I put those down here. So then I have a mass of 50 grams with some initial velocity, and it starts off such as the spring is unstretched, and the mass is given an initial velocity this way, and I want to find where the mass will be at 0.2 seconds. So if we think about this, we can call t1 0 seconds, and we want to use a time step of 0.1 seconds. So, and then t2 is going to be 0.1 second, and then t3 is 0.2 seconds. So I'm going to use my I'm going to use some approximations to find out where it is at t equals 0.2 seconds. So let's start with the very most important principle, the momentum principle. So this says F net, the change in momentum over the change in time, where the momentum is going to be mass times velocity. So if I write this out, I can say F net, going from time 1 to time 2, this is going to be P2, the momentum at time 2, which I don't know, minus P1, the momentum at time 1, which I can find out, right? I know, ooh, I didn't write down the velocity. V1 equals, I actually wrote this before, so let's say 0.1 negative 0.20 meters per second. So, but I do know V1, so I can calculate P1 over delta t. So then if I multiply both sides by delta t and add P1, I get the following. P2 equals P1 plus F net delta t. That is a super, super, super important equation. So important, I'm going to put a box around it, a purple box. Look at that. Now we have color. I like that. Now I'm going to need to find the force, but let's just move on for a second because I really care about the position. So where is the object going to be at time 2? Well, let's start with the definition of average velocity. It's the change in position, delta r over delta t, which is equal to r2 minus r1 over delta t. So r1, I didn't write it out, but I can find that. I'm going to find that for you. So I'm just working out the generic stuff here. So if I do the same thing, multiply by delta t and add r1, I get r2 equals r1 plus v average. Okay, but if I have v average, I could say v average is equal to p average. Oh, that's an arrow over m. So I'm going to write that as plus p average over m, because I just calculated the momentum. That's why I did it that way. Times delta t. Now I'm going to write one more form. So I know P1. I just calculated P2, so I can find the average, right? The average is going to be P1 plus P2 over 2. But I might be super lazy, and I'm okay with being lazy, and I may say, I don't even want to calculate the average momentum. I'm going to use the final momentum. So I'm going to say R2 equals R1 plus P2. What the heck, right? Can't stop me, over times delta t. And both of those together are important. I'm going to box them up too. And I'm going to do it both ways, and we can see which way works better. Okay. So what we have here is now I do need one more thing. I'm going to write it over here. Before I do this, I actually need to calculate the net force on the mass. So I actually have two forces acting on it. I'll draw them in red. Well, actually, I have not one at this point. I have the gravitational force, mg, and then there could be the spring force. I'll call it Fs. If it's not stretched, there's no spring force right now, but there will be. Okay, so let's write down an expression for the spring force. Mg is easy, right? Because g equals the vector 0, negative 9.8, 0 newtons per kilogram. So Fs, the spring force, is equal to negative k, the spring stiffness, times the length of the spring, L, the magnitude of L. So this vector, if I make a vector from here to there and call that the vector L, it's the same as R, right? Because that's where the position is. Minus the unstretched length, and I'll replace that with R. And then I need, now that's a scalar, that's a scalar, that's a scalar, that's a vector. So this is not a vector, so I need to fix that. And I want this to be in the direction of the spring. So I'm going to multiply this by the unit vector L hat, where L hat is this vector in the direction of the spring. Okay, and remember, L hat is equal to the vector L divided by the magnitude of the vector L. So in this case, I'm going to use R over the magnitude of R. But I can calculate a vector expression for the spring force. Then F net is just going to be that spring force, Fs, plus m times g, the weight. That's important. Actually, all of that's important. Okay. So here's what I'm going to do. I'm going to calculate the net force on the mass at T1, because I know all these positions. Actually, I'm going to calculate R1 first. Then I'm going to calculate the momentum at time T2 after 0.1 second using this formula. Once I know the net momentum, I know the initial P1, I can find the final momentum. Then I'm going to do this two ways. I'm going to calculate the position at the end of R2. I'm going to use the average momentum, and then I'm also going to use the final momentum, and I'm going to do it two ways we can compare. But what about at T3? Well, then I can just do the same thing again, right? I can, again, calculate the net force with the new position. It's a new position, so everything's new. Then I can update the momentum and find P3. I'd say P3 equals P2 plus F net delta T. And then R3, which is what I want, equals R2 plus P3 over M delta T. And I'll also use the average. Okay. So the first thing we need to do is, I'm going to start a new piece of paper, is to find R1. That's the one thing I didn't get. So let me move to a new piece of paper, and then we'll start cranking away at our calculations. Okay. So number one, R1. So let me redraw this picture. So really, I'm right here. This is 7 centimeters, and this is 30 degrees. So I'm going to write this. What's the x component of this? And what's the y component of this? If this is 7 centimeters, this would be 7 centimeters times the sine of theta, right? Because that gives me the opposite side. Remember, sine theta is the opposite over the hypotenuse. So the hypotenuse is 7. So I can write R1 as equal to, I'm going to write it out as 0.07 meters times the x component, which is going to be sine theta, sine of 30. The y component is going to be the adjacent side, so I'm going to need the cosine of theta. So that's going to be comma 0.07 negative cosine 30. And then there is no z component, and that's meters. So in this case, I put my origin up here, so you need to make sure that I manually add the negative sign for the y component of r. That is indeed important. Okay, so I have R1. I can start calculating stuff. Let's calculate FS1. It's just going to be negative k times the magnitude of this. And I'll go ahead and tell you, if I take this squared plus this squared, square rooted, the cosine sine squared are going to turn to 1, and I'm going to get 0.07 meters. Minus the unstretched length, 0.07 meters, times the unit vector, which who even cares, right? Because this is 0. So this is equal to 0, 0, 0 newtons. Now I can calculate F net. F net is going to be equal to M, which is 50 grams, 0.05 kilograms, times G, 0, negative 9.8, 0 newtons per kilogram. Now I can calculate P1. So P1 is going to be equal to, remember my velocity right here, it's going to be my mass, 0.05 kilograms. I'm going to leave off the units. 0.1 negative 0.20, and this will be kilogram meters per second. I'll put it at the end. Okay, now I am all set to calculate P2. P2 equals P1, which is this, 0.05, 0.1, negative 0.2, 0. That's P1 plus Fnet, which is this, 0.05, 0, that's a vector, 0, negative 9.8, 0, times delta t, 0.1. So then I have a vector for V2. I'm going to calculate that. And you can do that with your calculator, right? So I can do the x component. It's going to be, yeah, that is. So it's going to be 0.05 times 0.1 plus 0.05 times 0 times 0.1, which is, that's easy to do. And then this one's going to be all the y components multiplied and added together and so forth. Okay, so now I'm going to do R3, R2. It's going to be R1, which I just wrote down, 0.07 sine 30, negative 0.07 cosine 30, 0, plus P2, which I haven't calculated yet, so I'm just going to write that as P2 over M, which I do know, 0.05, times delta T, 0.1. Now, what if I wanted to do it the other way? I could replace this with P average. P average is going to be P1 plus P2 over delta T. And if you think, boy, golly darn it, there's a lot of numbers here, you're right. And I'm going to show you something we're going to do. But I just calculated R2. Now what do? Now I go all the way back up here. I recalculate the net force. I recalculate the momentum at 3 and so forth. I need to redo all those calculations, and I'm going to do those. You can do those on your little calculator if that makes you happy. You can go down here and start typing away, calculate, calc. But I'm not going to do that because I'm super lazy. So instead, I'm going to switch over here. So I'm using my Python, and I'm not going to write a numerical calculation. I'm not writing a program. Okay, I'm just writing using this to code. So let's just start entering our values here. So I have, let's just put on everything that I wrote down before. M equals 0.05. I'm not going to put the units because I'm trying to go fast. dt equals 0.1. L0 equals 0.07. K equals 5. R1, I already wrote that down. It's going to be 0.07 times vector. I should put theta first. Let's do this. Theta equals 30. But I need it in radians because Python uses radians. So it's going to be times pi divided by 180. So it's going to be vector sine theta negative cosine theta 0. You like that? Okay, V1 is going to be equal to vector 0.1 negative 0.2 0. What else do I need? G equals vector 0, negative 9.8, 0. I think I'm good to go. So let's I calculated R1. I have R2. I can calculate the net force. Let's say F net. I'm going to put it as 1 just so we can keep it simple. It's going to be I'm going to write it out. Negative K times the magnitude of R1. Mag R1. So remember in Python, I can use the mag expression and it gives me the magnitude of a vector. I don't have to do it manually. You could if you wanted to, but we don't have to. Minus L0, and then I need to multiply that by the unit vector R1, which also is in Python. I can say norm, not norma, R1. Now I need to add in M times G. Now it's plus M times G, okay? Because it's F spring, all that's F spring plus the gravitational force. Yes, it has a negative y component. I've already included that, right? I don't need to put negative here. Don't do that. This is a vector equation. That's a vector, that's a vector, that's a vector. Okay, so I calculated F1. Now I can calculate P2. So P2 equals, oh, I didn't do P1. What the heck? Okay, P1 equals M times V1 there. P2 equals P1 plus F net 1 times dt. If you want to print it out, you can. Print P2 equals P2 kilogram meters per second. Let's run it because, you know, spring manual calc. I'll give you the link to this code also. Save. Run it. Okay, so there's my momentum P2. You can check your math. Now I'm going to find, I'm going to go ahead and find P2 average. Okay, p average 2, I'll call it p average 2, because I'm going to have another one. And this is going to be p1, it's going to be p1, which is a vector, plus p2, which is a vector, divided by 2. You can do that. Okay, now I'm going to say r2 equals r1 plus, I lost it here. Let's do the p average 2 times dt divided by m. And let's print that. R2 equals R2 meters. And then let's do it again. R2 equals R1 plus P2 times dt over m. And let's print it again. In Python, you can recalculate something that just goes with your last value. So I'm going to say print R2 equals R2 meters. And let's run that. It's nice to run it in the middle. So I got, notice here, okay, in the x direction I get the same thing. In the y direction I get something slightly different. The first one is actually a better value, but it's good. If you did it either way, I'd be pretty pumped up. Okay, so now I did it. I calculated R2. I have the new value. Now I can go back and do it again. I'm just going to start up here. I'm going to calculate. I'm just going to copy this. Watch this. Copy this. I should just copy the whole thing, and I'm going to change this to fnet2, and that's going to be R2, and this is going to be 2. The gravitational force is the same. Let's print that just for your fun. fnet2 equals fnet2 newtons. Run it. There you go. Now I'm going to find P3. P3 equals P2 plus fnet2 times dt. I'm not going to print it. I'm getting bored of that. I'm going to find P average 3 equals P2, parentheses, P2 plus P3 divided by 2. And then I'm going to calculate R3. R3 equals R2 plus P average 3 times dt divided by m. I will print that. And that's in meters. And then we'll do it the other way. R3 equals R2 plus P3, oh yeah, times dt divided by m, and print that again. And let's run that sucker. And you see we get slightly different answers, but it's not that bad. It's really not that bad, okay? And if you made a smaller time step, it would be even better. But there you go. That's it, right? So I've done it manually. You could do this on your calculator if you wanted to, but it's not that hard, okay? It's just a lot of tedious work. And this is actually why we want to do this have the computer do all of the calculations. And I'm going to show you that in the next video, but I wanted to give you a more detailed view here. So I'll talk to you guys later.